light speed travel and why it leads to time paradoxes. We have a multitude of names for faster than light speed or FTL space travel in popular science fiction, including hyperdrive, warp drive, and Holtzman drive. Unfortunately, even if we are able to attain such speeds, going to our nearest neighboring star system is a distant fantasy that would take us about 6,000 years to complete. So, how will we ever be able to develop technology that allows us to travel over the entire galaxy in a single lifetime or less? Maybe, maybe not, because we aren't supposed to. Why though? Come along and let's dive deeper into the nitty-gritty of how and why traveling at the speed of light causes time paradoxes. What do you know about the speed of light? The ability to travel at the speed of light is a common topic explored in science fiction. Despite how unbelievable it may sound, the speed of light is measured to be 299,792,458 meters per second. More than 7 circles of Earth may be completed in a single second, making interplanetary travel possible for humanity. In 1947, humans took their first flight at speed greater than the speed of sound, which was the first step toward achieving human-made supersonic flight. This cleared the way for subsequent generations of supersonic aircrafts, including the commercial Concorde jet. If civilization continues to advance, would it eventually be able to travel at the speed of light? Sadly, not at all. Or at least not within the bounds of what we now know about the physics and the natural world. The famous equation E=mc² that summarizes Albert Einstein's theory of special relativity states that the speed of light is effectively a cosmic speed limit that cannot be exceeded. Consequently, traveling at or faster than the speed of light is physically impossible, particularly for mass-bearing things like spacecrafts and people. The quantity of energy, E, necessary to approach the speed of light is a substantial obstacle to the viability of light-speed space travel. This limitation applies even to extremely small entities, such as subatomic particles. Protons, which are atomic particles, have been accelerated to a speed within a hair's breadth of the speed of light thanks to the Large Hadron Collider, LHC, the world's largest and most powerful particle accelerator. Even a single proton would need almost endless energy to approach the speed of light, which is information that we have not yet uncovered. Next, how do we increase speed to travel almost at the speed of light? On May 29, 1919, exactly a century ago, observations made during a solar eclipse supported by Albert Einstein's general theory of relativity. The particular theory of relativity that Einstein developed previously significantly impacts how we understand light. It acts as a reference for researchers investigating the important subject of particle mobility in space, which is essential for maintaining the safety of spacecrafts and people. When traveling through a vacuum, the constituent photons of light are said to maintain a constant velocity of 670,616,629 miles per hour, as predicted by special relativity. This extremely high speed cannot be achieved, and there will never be an increase above the current level of capability. Acceleration of particles to speeds near or exceeding 99.9% of the speed of light occurs everywhere across the cosmos, from the interiors of black holes to the region immediately around the Earth. One of the primary goals of NASA is to investigate what exactly causes these particles' acceleration. The investigation of these extremely swift or relativistic particles can help future expeditions to the moon and other heavenly bodies and shed light on our neighborhood in the galaxy. If a large number of particles moving at near light speeds were to impact onboard equipment at once, human beings could be put in danger of being exposed to hazardous radiation while on a journey to the moon or beyond. The following explains each of the 3 mechanisms that contribute to the increased speed. 1. Electrical and magnetic fields. Most means for accelerating particles to relativistic speeds employ electromagnetic fields, the same force that keeps magnets on your fridge. Particles are propelled at great speed throughout the universe by a mix of electric and magnetic forces, which function as opposing forces. In the same way that gravity pulls on heavy objects, electromagnetic fields pull on charged particles, driving them forward at tremendous speeds. In some situations, electromagnetic fields can accelerate particles to nearly the speed of light. Electric fields are routinely utilized on Earth for the specific purpose of speeding particles in controlled laboratory conditions. Particle accelerators, such as the Large Hadron Collider and Fermilab, employ pulsed electromagnetic fields to accelerate charged particles to nearly the speed of light. Collisions between particles flying at these speeds can produce enormous amounts of energy. This opens the door to the hunt for elementary particles and studying conditions in the universe immediately after the Big Bang. Number 2. Electromagnetic explosions. Massive, audible explosions occur all the time in the Earth's orbit. When twisted magnetic fields snap and realign, generating explosions, particles are propelled into space. NASA's Goddard Space Flight Center Scientific Visualization Studio, Goddard, related video download. Magnetic fields surround us on Earth and extend across the solar system. Even charged particles in space are steered by the fields and travel in a spiral pattern around them. When these magnetic fields collide, they can become entangled. The lines will rupture and realign explosively as the strain between them increases, a phenomenon known as magnetic reconnection. When a region's magnetic field abruptly alters, it generates electric fields, which accelerates the charged particles in the area. Scientists suspect magnetic reconnection as a mechanism of accelerating particles such as the solar wind to relativistic speeds. Very fast particles close to the planets have various unforeseen consequences. When the sun's magnetic field collides with the Earth's magnetosphere, localized regions of magnetic reconnection form. When the Earth's magnetic reconnection occurs on the night side, particles are released into the upper atmosphere, where they may spark auroras. In a slightly different approach, magnetic reconnection is thought to be to blame in Jupiter and Saturn's atmospheres. NASA's magnetospheric multi-scale spacecraft was designed with one objective in mind: to learn as much as possible about magnetic reconnection. The results of the data analysis can shed light on how particles accelerate to relativistic speeds on Earth and beyond. Number 3. Wave-particle interactions. The collision of a particle with an electromagnetic wave which causes the particle to speed up is an example of what's known as a wave-particle interaction. Electromagnetic fields have the potential to be compressed when two waves collide with one another. By bouncing between the waves, charged particles can generate energy in the same way as a ball might gain speed by bouncing between two falling walls. The continual acceleration of particles in near-Earth orbit caused by these types of interactions might cause damage to the electrical components of satellites and spacecrafts. The Van Allen probes are just one example of a mission carried out by NASA that assists us in better comprehending the dynamics of wave-particle interactions. Interactions between waves and particles have been hypothesized to be the driving force behind the acceleration of some extrasolar cosmic rays. Following the detonation of a supernova, a shell of hot, dense gas is expelled from the star's center, creating what is known as a blast wave. These bubbles, loaded with magnetic fields and charged particles, function as launch pads for high-energy cosmic rays that are accelerated to a speed that is 99.6% that of light via wave-particle interactions. Interactions between waves and particles may cause a change in the velocity of solar wind and cosmic rays coming from the sun. Next up, can anything travel at the speed of light? In 1676, Danish astronomer Ole Remer calculated that the speed of light has a maximum value by examining the orbit of Jupiter's moon Io. According to the American Museum of Natural History in New York City, the Dutch mathematician and physicist Christian Huygens was the first to attempt to prove the true speed of light 2 years later, utilizing data obtained by Remer. Light travels at incredible speeds, as demonstrated by Huygens' calculation of 131,000 miles per second, 211,000 kilometers per second, which is incorrect by modern standards. We now know that the speed of light in the vacuum of space is approximately 186,282 miles per second, or 299,792,000 kilometers per second. According to Albert Einstein's particular relativity theory, nothing can travel faster than the speed of light in a vacuum. Jason Casabry, Associate Professor of Aerospace Engineering at the University of Alabama and Huntsville's Propulsion Research Center, confirmed, "We cannot go faster than the speed of light across the vacuum of space." Claudia de Rham, a theoretical physicist at Imperial College London, told Live Science via email that technically the expression "nothing can go faster than the speed of light" isn't quite correct by itself, at least in a non-vacuum situation. She did, however, mention several caveats to keep in mind. Because light possesses qualities of both particles, photons, and waves, it can be thought of as both. The concept of wave-particle duality describes this phenomenon. Because light is a wave, de Rham believes there are many reasons why some waves can propagate over a medium faster than white or colorless light. She attributed this fact to that when the light goes through a medium, such as glass or water droplets, the different frequencies or colors of light travel at different rates. The most prominent example is rainbows, which have longer, faster red wavelengths at the top and shorter, slower violet wavelengths at the bottom, as stated in a post by the University of Wisconsin-Madison. This is not the case with light in a vacuum. Because they are all electromagnetic waves, all kinds of visible light travel at the same speed in a vacuum, 3 times 108 meters per second. The same way may be said for gamma rays and radio waves. Rhett Allain, a physics professor at Southeastern Louisiana University, emailed Live Science about it. As a result, Durham believes that light is the only thing capable of traveling faster than the speed of light, but only when it is not in a vacuum. The maximum speed of light is 186,282 miles per second, and it remains constant regardless of the material it passes. Following that, the warp drive. The thought of interplanetary travel becoming a reality in human life has captivated both the scientific community and popular culture. Any speed up to and incurring the speed of light is permissible for space travelers, as long as it is consistent with special relativity. If someone were to accomplish this, they would experience time dilation, allowing them to travel from Earth to any star and back in an arbitrarily short time from Earth's perspective. When they returned to Earth, they discovered that their friends and family had aged far faster than they had. This phenomenon is known as the twin paradox, and it is well known. Miguel Alcubierre recently proposed a warp drive metric in which a starship might go to a star d light years away and return in less than 2d divided by c time, where c is the speed of light. Even more astounding about this space-time is that the time spent in space correlates precisely to the time spent on Earth. In any local region, the spaceship does not exceed the speed of light. The spacecraft can even rest in the warp bubble's interior. The ship is carried along by space-time while being at rest locally. In the same way, galaxies are receding from each other at incredibly high speeds due to the universe's expansion. The warp drive uses this type of expansion to achieve faster than light travel and contraction. Next, let's look at the effects of traveling faster than light. Even though science fiction has a propensity to gloss over or simplify a fundamental violation of physics, faster than light communication, which includes travel, breaches something difficult for people who are not physicists to comprehend. In other words, if travel at FTL speeds is allowed, the chain of causality will be broken and it will be possible to travel across time. It would appear that the laws of relativity and causality govern the universe. Consequently, neither the speed of travel nor communication can exceed the speed of light. But this begs the question, why is this the case? Why is traveling at the speed of light necessary for time travel? To better illustrate this point, it would be helpful to produce some diagrams. Diagrams of space-time will serve as our primary method of data collection. They look like this. This is an attempt to illustrate the 4 dimensions of space and time that make up our universe. Since then, I've completely lost the ability to depict space-time in all dimensions. Because this is a flat screen, it is impossible to draw the number 3. Consequently, I have made 2 dimensions of space appear to be a single line, and I have portrayed the entire space as a single line. Although it won't make much of a difference in the grand scheme of things, it's important to keep in mind. Moving on, the space diagram. Here's my space-time diagram to prove my claim. Because I am at rest in the center, time moves orthogonally, or at right angles, to the spatial directions originating from my position. You will notice that other people's space-time diagrams and time and space axes differ from mine. That is, after all, the basic concept of relativity. The speed of light is universally measured to be the same under special relativity. For example, we can assert that light moves at a 45-degree angle to the time axis in every space-time diagram. Null lines represent light's pathways. At this moment, which I'll call t equals 0, I'm showing the light lines that didn't pierce anything when the time and space axis cross. Remember that I'm shutting off a lot of space, so these light beams are coming from all directions around me. If we suppose that light travels at a 45-degree angle, anything moving slower than light from this t equals 0 event will be closer to the time axis than the light beams, and anything moving faster will be farther away. Those light beams will become the light cones of the future. This is the collection of space-time events that can perceive the events at t equals 0, and, by extension, all the events that can be influenced by whatever happened at this event at t equals 0 in a universe without FTL travel. The past light cone in a universe without FTL is defined by the 45-degree lines that extend backward in time from the event, and it includes all the events that could have affected the t equals 0 event, because the light, and thus the things moving slower than light, from those other events had time to reach the t equals 0 event. Now that I've covered the fundamentals of space-time diagrams, I'll give an example of demonstrating why FTL requires time travel. Consider this concrete example. Suppose humanity has established a means of communicating with the people of Proxima Centauri b, a planet located 4.25 light-years from Earth. Here's another example of a space-time diagram displaying FTL and slower-than-light communication technologies. More specifically, I've drawn proximal Centaurian time perpendicular to our own. This is owing to the constant relative velocities of Earth and Proxima Centauri. The differences are minor compared to the speed of light. Humans and Proxima Centaurians have no significant relativistic effects when keeping track of time. Let's imagine something happens far from Earth, but an angle that allows light to reach us before Proxima Centauri. In the space-time diagram I've created, that would appear like this. We must first comprehend the light before it can reach Proxima Centauri. Please remember that the event's light rays are drawn at a 45-degree angle to my time axis. It is still light, and light moves at a 45-degree angle in space-time diagrams. We'll then consider fast-to-light communication. We quickly contacted the proximal Centaurians through FTL phone to inform them of the occurrence. They have years after receiving the phone call to prepare for the event's illumination. For the sake of argument, let's say it's a supernova or the launch of relativistic attack vehicles. We are employing science fiction cliches. This is how most people today envision interstellar communication. There doesn't seem to be any problem here. Everyone agrees that the event happened first on the Earth, known as Proxima Centauri, and that the light finally made its way there. Although the proximal Centaurians learn about the incident early, there is no casualty violation. We can all agree on the chronology after all. Nothing happens unless there is a cause for it to happen, right? However, we overlooked relativity. This only works when everyone travels in the same direction relative to the rest of the universe, like Proxima Centauri and us. So to show the problem, let's add a third observer moving at extraordinarily high speeds compared to Earth and Proxima Centauri. For science fiction, a relativistic spaceship is included. Its journey on my space-time diagram is significantly asymmetrical about my time axis, because VC, but V is less than 0. Following that, the casualty violations. Relativity's effects can be felt here. According to relativity, anyone traveling at a constant pace has every right to consider themselves immobile. This gives us the impression that we are entirely still, ignoring the Earth's rotation or its orbit around the Sun. They assume they have achieved peace, but the proximal Centaurians know better. On board the relativistic spaceship, humans think they are immobile, so that they can draw a space-time diagram that contains their understanding of time. Both of our senses of time are always focused on the ship. That leads me to conclude that their ship's trajectory corresponds to their time axis. They also share the possession of a space axis with me. Because relativity confuses time and space, I consider their spatial axis bent. I won't show that the space axis is reversed across the 45-degree zero line, but that appears to be the case. Traveling observers see a peculiar merging of space and time and an unexpected facet of relativity. This is the only way to secure a universal agreement on the speed of light. Now I can see the spaceship's space-time diagram from its point of view. Space and time would be distorted. Light from the event would have moved to a 45-degree angle and Earth's axes would appear. It all comes down to perspective, or relativity. However, such a diagram is excessive for our topic. Therefore, we will skip it. What is the question now? The spaceship's view of the timeline. For this purpose, the ship's constant timelines must be known. That's easy to understand. In our space-time model, constant timelines are perpendicular to the space axis. That's the end of the spaceship. They always have the following timelines. Do you see the problem now? Because we can see the event's light impacting our planet, we assume this sequence of events is correct. We dialed Proxima Centauri on the FTL phone. Proximal Centaurians respond to the summons uniquely, finally emerging into the light. What is the ship a witness to? They see the phone call from Proxima Centauri being received, and then they notice the earthbound call coming through. The law of cause and effect has been violated. If properly designed, the ship's FTL phone may allow it to call Earth before Earth calls back. Hey, don't make that call to Proxima Centauri we just watched you make. They could warn Earth. What happens next? We can now hear your thoughts. Wait a minute, the speed of light has a maximum value. They won't be able to see the scenes you just showed them because they don't yet exist in the time frame of the spaceship. That is our only hope for survival. Unfortunately, no. The ship begins to see the bigger picture at this point. The light from the answered phone call arrives before dawn from the phoned number. Casualty has been broken again. You can see the problem now. If we could assert that there is just one frame of reference for establishing cause and effect, we could have FTL without worrying about casualty. If relativity is correct, there cannot be a single reference frame. We may all agree that relativity is true since the speed of light is always measured to be constant. You can time travel or converse in reverse if you can travel faster than light or have a conversation with someone who can. And since that does not appear to be the universe we seem to be living in, this is cause for alarm. Finally, the time paradox. You want to make a difference in the world, don't you? Think about the impact your grandparents' love and support have had on you. The grandfather dilemma can be illustrated by the following scenario. You decided to kill your grandfather when he was still young. Although you adore him so much, you must participate in this research study since you have no other option. To put it another way, you won't be around to murder your grandfather since your grandmother won't be around to give birth to your parents. And therefore, you won't be around to murder yourself. Oh boy, what a striking contrast it is. When considering the full extent of the challenge, we must consider virtually every alteration our hypothetical time traveler will bring about in the past. It is difficult to predict how the planet you come from will be affected by the choices you make in this chaotic universe. It is difficult to foretell the long-term repercussions of even the most dramatic action, such as murder. This is analogous to the way that the flapping of the wings of a butterfly in the Amazon can produce a tornado in Texas. It is feasible to find a solution to this issue, but doing so would eliminate free choice. The capabilities of our time traveler are restricted to what has already taken place. It's okay, you won't be able to hurt Grandpa or start a fight because everything you've done has already taken place. There is a chance that the time traveler's actions triggered a schism. Don't be concerned about that. In reality, leading to the existence of two parallel universes, one in which the time traveler was born and the other in which he did not kill his grandfather and was therefore never born. When information from the future is brought into the past, a conflict similar to the one described above arises. Let's imagine that a time traveler from the future with good intentions informs me that a grand piano is about to fall on my head in the street, or that I have a sort of cancer that can be cured if detected early enough. If I were given this information in the future, I might be able to take precautions to avert the impending catastrophe. However, going back in time and sending back the information that eventually saved my life would be pointless. If I were to be given this information in the future, I might be able to take precautions to avert the approaching catastrophe. A further inconsistency. So, what do you think? Is FTL possible? Leave a comment in the section down below. Don't forget to like and subscribe too. Thanks for watching and have an awesome day.